So why deep learning? So compared to traditional machine learning methods like clustering, regression, also the classification methods, which are most supported by mathematical series, those are not good at handling high-dimensional data. Whenever you have an increase of dimension, the amount of data need to be processed will be huge to get any reasonable results. And also, it's difficult to extract features automatically. Someone gives you a picture with circles and triangles, and you need to have some manually extract features to do the scanning to figure out if there is a circle or a triangle in the picture. So those features you are creating manually are called filters or kernels. Those should have been done manually in a traditional computer vision and machine learning methods. With deep learning, all those could be done automatically. So you don't need to manually provide a filter to identify and locate a certain object in a picture. The deep learning methods can train your model so that the model can automatically detect certain features. And we'll talk a bit more about those later in this module. So another big advantage of deep learning is that it's computationally, even though it's computationally expensive, but it's capable of handling dimensional datasets really efficiently nowadays, especially on GPUs and other specially designed hardware. Because a lot of manipulations in deep learning methods are more or less like matrix addition and subtraction, multiplication. Those could be highly optimized computing devices, especially those on GPUs and TPU, tensor processing unit done by Google, and GPUs mostly by NVIDIA, and also AMD is also doing that, and Intel also providing GPUs that can handle very, very compute-intensive analysis and matrix manipulation. Well, that's the reason why the deep learning is getting really popular nowadays, because it's really solving our daily problems. And deep learning is one class of machine learning, as we talked previously. And it's just using a group of layers, and there are some non-linear processing unit in between. And using all these objects, I would say layers and activation functions, you can put together different architecture of neural networks to handle different problems. So deep learning is a supervised learning. Basically, you need most of deep learning methods are supervised learning. There are also some unsupervised learning methods or semi-supervised learning methods, but today we'll be mostly focusing on supervised learning. For most of the classification problems, it's definitely supervised learning methods. You need to tell the model that your data belongs to a certain category. So when you train your model, you can keep track of the errors you're making and then make adjustment accordingly, so that your model could be tuned to best fit your data. The machine learning method, especially deep learning method, can learn multiple levels of representations that can represent to different levels of abstraction. We'll talk a bit more about this in the convolution neural network example, because when you do the downsampling, we call him pooling, max pooling, average pooling. We'll talk a bit more about those. It's more or less like a downsampling method. Using that, if you keep your size of a kernel unchanged, when you downsample your image, you're more or less like scaling up your filter. So a small circle can cover 3 pixels or 5 pixels, and it could be covering a big area in your original image after you do the downsampling. So a very important trick in doing machine learning, especially deep learning, is to figure out a good downsampling algorithm. And max pooling that will be used in our examples is one of the methods that are used by a lot of data scientists and model builders to do the downsampling. We'll talk a bit more about that today as well. So the deep neural network, also artificial neural network, they are inspired by the biological phenomena or biological objects. The diagram of the neuron shown to the left here contains multiple components. You have the terminals, you have a dendrite, you have axon terminals. So the neurons are transmitting signals through those terminals with electronic signals. It's more or less like an activation function in the deep neural network. And every neuron here, represented by a very small circle in this diagram, it's able to transmit information from one layer to another layer, from one neuron to another neuron. And in between them, there will be an activation function called to decide if this neuron contributing enough to be transmitted to the next layer, or it will be just hidden out from the transmission. The multi-layer perceptron that is represented by the diagram to the right here is one of the simplest neural network. It has a densely connected layers of neurons just like the one showing on this diagram explicitly. So you have input and output. You have more than one layers of neurons in between, and all the neurons in the layers, they are connected, fully connected to all the neurons in the neighboring layers. So that's so-called multi-layer perceptron, a simplest version of neural networks that could be used in many simple applications. For example, when you're trying to do regressions and some other simpler models, you can directly use multi-layer perceptron or dense layers to construct your neural network. So the examples we'll be covering today is mostly on images. So it's good to look at the images to get started. When we look at this image to the left here, we saw you probably see the cat, and you see all bushes, or you see probably a house in the background. But for computers, they don't see what we see here, because for computers, they are just seeing all the numbers. And those numbers are arranged in 3 channels. If you're familiar with the data stored in images, you probably know that we have 3 channels stored in the color image, mostly. Sometimes 4 channels. The last channel will be controlling the opacity, how bright the channel should look like. All the other 3 major channels are RGB, red, green, blue. So each channel goes from 0 to 255. And the higher the value is, the brighter it is. Otherwise, it's getting darker. If you get a 0, 0, 0, you get a black spot. If you get a 255 or 255 for RGB channels, you get a white spot. So that's the data that a computer can see. Now, the question we are going to solve, the problem we want to solve with a deep neural network is to take this input image and output a vector with 4 elements. Here, I'm just want to be very specific for this particular problem. We have a group of images with a dog, cats, hat, mug, 4 different types of images. We have probably hundreds or thousands of images in each category. And we want to train our machine learning models to tell us what the image contains, what's in the image. And given this picture, we can see that even just for one channel, we could have thousands and thousands of numbers like this. To go from that big matrix to just 4-element vector to a 4-element vector, we need to do a lot of reduction of the dimension, and we need to do a lot of downsampling, which is equivalent to reduce the dimension. And then we need to do a lot of information extraction. And it works just like magic here. Basically, given the data and by training the neural network, we can tell the probability of a certain category. And the reason why it works is that we have this deep neural network with so many parameters we can tune. And every time an image passes through this neural network, we notice some errors, and then we tune the parameters to make this error smaller. So you can consider this more that's like a function mapping. You are trying to find this function in between x and y. You want to map a very big array to a small array, a very small array. The very big array here, I'm just representing the image because you can flatten out the 2D array, like the one showing to the left here, into a 1D array. And this function is just taking this extremely large 1D array and compress that into a smaller, very, very small 1D array. And this function needed to tell us what this output should look like and how is that compared to the expected output. If the error is big, we needed to go back and tune all the parameters in this function to make that mapping matching with expected output as close as possible. Before we jump into the mathematical questions about how this backward propagation and all the optimization work, it's good to look at this problem at a very, very intuitive way. Let's consider we have a data set which is showing in this rectangle to the left here. That's a data set we're going to use. Every row here is we can consider it's an image, or it's just input data. And all the circles here in this data set box are the expected output. For example, you can consider the dark blue horse and light blue cat, and a white circle representing probably a hat or something like that. Then you can consider all the boxes in that dataset rectangle. Each one is just a pixel of the image you have. You just flatten it out. You take from the very top first one, then you read all the way to the right, then you start to the second row and read again. So you flatten out all the pixels in the 2D image and make it a 1D array. So that's how you get all the data prepared. Now we have 4 images, for example, and I want to train my neural network so that my neural network can recognize each image correctly. To get started, I have this data at the bottom here, at the bottom of the neural network. And then I have multiple neurons, and then finally I have a output. I just put in one layer here, which is not a deep neural network, because when you call some neural network deep neural, you have at least 2 layers. But here I just want to show this one layer, for example. You can continue with extra layers. All the weights and biases you put into this layer with all the white circles in the diagram in the middle, those could be just random initialized for all the neurons. Those are just random numbers. So when you input your first image and try to get some output here, you are guaranteed to get some random number because all the weights and biases are just random. You can simply take the weighted average for the first circle, get the neuron output, then get the weighted average of all the pixels for the second one, and then finally you get to the output, which will be just a random number to get started because you don't have anything predetermined in all the circles. So the weights on the neurons are randomly generated. And when you get the predicted output with all the random numbers, you get some random number. Then you subtract your expected output. Then you get a number 5 here, showing at the bottom. So that 5 just means that there's some error here. You don't have any information about what you want to do about it. So it's just a measure about the error you currently have compared to the ground truth. Okay, now the tricky part comes in next. So to decide how we want to tune our weights on each neuron in our neural network, we first increase the weight for the leftmost neuron. Let's increase the weight by 50%. Let's increase that a little bit. Now, after you increase the weight of the neuron to the very left here, and you use the same data, input data, and plug it into your neural network, then you get another output. This time it's not completely random because all the other neurons, they are fixed. You're not changing them anymore. Even though they're starting with random numbers, you're not changing them anymore this time. All you changed is the weight of the neuron to the very left here. As you can see, the line getting thicker, the purple line getting thicker. It's representing, I'll take more weight from that particular neuron. By doing that, you notice that your error is getting bigger compared to the previous one. So what does that mean? That when you increase weight of the first neuron, your error is getting bigger. That means this first one shouldn't be contributing much to your expected output. Otherwise, your error will be getting bigger. If you keep increasing the weight for the first one, your error will definitely getting bigger, at least based on what you see here. So a good guess to tune your model is to reduce the weight for the first neuron here. And we'll see if it's getting better or not. By reducing the weight for the first neuron, you notice that the error is getting smaller, which is a good sign. So you keep it there, and then you continue doing this for all the other neurons, one by one, until your error is getting smaller to some extent. Okay, you can continue doing this for more than one images. You can do this for all the images you have, and you can do this for all the neurons you have. So there will be a lot of tuning here. And fortunately, we have computers to help us with all this. We don't need to do this by hand all the time. We just write a program and let the computer handle all the tuning and calculation for us. And this could be done very effectively and efficiently if you write this into the matrix multiplication form or matrix form. And matrix addition, matrix multiplication could be done very efficiently with computers nowadays. It looks like very labor intensive, but with the help of a computer, this could be done very, very efficiently.